Thanks. I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for these students and for the break which is about to start. Just help us to, again, Lord, glorify you what we do, Lord. In your name I pray. Amen. So I, of course, owe you a few examples on how to apply the isomorphism theorem. I think I'll make a little video about that, since otherwise this lecture will end up getting corrupted from it, and it would just be bad. So I'm going to start on lecture 16. And this lecture is on group actions and the orbit stabilizer theorem. If you look on the YouTube, you might have noticed that there is a pretty famous series of lectures on abstract algebra by Professor Gross of Harvard. And those are based on Artin, I think's algebra. And if you watch those, what you'll find is that he introduces this concept of group action early on. And the whole course is really painted with this brush, so to speak. It can be used as a unifying and sort of clarifying idea throughout the course. And we don't take that approach, right? I mean, I'm talking about group actions now. Here we are, lecture 16, right? But this idea is really the other idea about group theory, namely that we think about groups as transformations on other objects. So we've looked at groups primarily from what? The perspective that, well, I suppose in some sense they're kind of like numbers, right? They're these sets of things and we can study their properties and do things to them. But we don't too much think about the idea of a group acting on something else, right? Not up to this point anyway. And that's what we're going to do today, is talk about how you sensibly talk about a group acting on another object and what that means formally. All right? So we'll begin with the definition. And here it is. Let G be a group and S a set. Then an action of G on S, which I called a multiplication in the notes, but that's fine, defined by, I mean, you could call it a multiplication if you wanted, but I'll say an action here, defined by star, going from G cross S to S, is called a group action. Oh, that's why I called it multiplication. A function. Well, no, it's an action. It's called a group action. I'm sorry, my language now. Now I realize I shouldn't have crossed out. That's why I said multiplication there, is to avoid this awkwardness, but oh well. Par for the course today. Group action of G on S if for each X in S we have two axioms hold true. Number one, E times X is equal to X for E, the identity in G, right? And two, I'd say associativity, but it was not quite associativity in general, if you think about it, because we're talking about A star B star X. And this was not associativity because you notice that A and B are group elements here, but X is a thing in a set, all right? And that doesn't have to be a group element. This is not associativity. It's kind of like associativity. It's, I'll just say that. So multiply AB first, and then in the group, of course, and then act on X for all AB in the group. So these are the terms and conditions, what it takes to have an action of a group G on a set S. All right? So let me list some examples for you. And I will try to resist the urge to get into all the details for the examples, because I want to see the forest for the trees here. So if we have G is a subgroup of the permutations on some set S, right, then we can define sigma acting on X by just sigma of X. So this will define an action of a subset of permutations on a set. 2. You could have H a subgroup of G act on S equals to G. So in each one of these cases, I'm going to try to indicate both the group which is acting and the action. All right. So the way we're going to have the subgroup act on the group is by the following rule: H times X equals to HX. This defines a action. This would be an H action on G. We could use that language, an H action on G. What is it? Oh, nothing? Okay. Okay. All right, the lack of detail is bothering me. Let's pause from my lack of detailed list and just dive a little bit deeper into number 2. So what would, E times X, what would that be? EX, right? Which by definition of identity in the group, because H is a subgroup, we have E is the identity for the group, and on the other hand, the associativity. In this case, associativity, I think actually boils down to, well, associativity of the group, right? Because this is AB times X, yeah? Excuse me, this, I shouldn't just assume it. Let's work through it, yeah? All right, so we're trying to get to what I just wrote, but we should actually get there. So to start with, this would be A times what? A times, what's B times X? This is BX, right? By our definition. And then what's A times BX? Well, that's A times BX, yeah? By definition of the group action again. And then this, by associativity of the multiplication in the group, is that. And then what's the definition of star here? Well, this is exactly AB star X. And that holds for arbitrary X. Therefore, axiom 2 holds for this alleged group action. Indeed, it is a group action. So we can let a subgroup of a group act on the whole group. Well, that will never be abused, I'm sure. Have you guys ever looked at your Social Security card? Do you know what it says on your Social Security card in the back? Not for purposes of identification. How many times have you ever been held up in your life for not knowing your Social Security number or having a Social Security card, and yet the government has the audacity to still print on the back of those cards, not for purposes of identification? Never trust the government. All right. So, also, so another group action we can define is this. So just because you have a group, you have a group, you have a set, there may be more than one way for the group to act on the set. This is another way that H can act on G. We can multiply on the right by H inverse. And in here, I think it's worth going through, let's go through associativity again. So if I have, AB dot X, why does that actually work out? Well, that's X times AB inverse, which is what? B inverse A inverse by sock shoes, right? Which is, by the way, B dot X. A inverse, which is, by the way, A dot B dot X. So there's axiom 2. This is another F2 cell phone. Let's see here. Shut up. Yes.
Okay, I have a question. Why? I feel foolish asking this, but on your last example in the red,
Uh-huh.
how do we know that B is not transforming X in some way such that, like, why are we allowed to simply...
The definition of H star X is HX. So I'm merely using the definition of the action as set forth right here.
Okay, and so then you use the fact that multiplication is associative.
In the group, yeah.
Okay.
Yeah.
So in the first example, is it G acting on, like it's always the subgroup acting on the group, or is it
Well, this one, so here the group which is acting is the subgroup
in two?
in 2, and also 3. The set is the group which is acting is the subgroup in these both of these examples. This also defines a so-called H action on G. So you could take group action and replace it with the more descriptive G action. That's in some sense a better terminology because it's more precise, right? It tells you which group is acting. And when there's more than one group in play, well, maybe that's a nice language to have, yeah? So we can also take the set to be the field F and take the group to be the group of units in the field, right? The non-zero elements of the field. And in this case, an example, you might notice that 1.x equals to x, and also ab.x is equal to a.b.x. What I'm trying to say is that the ordinary multiplication of numbers in a field gives you an example of a group action, right? Just ordinary multiplication is a group action there, yeah.
So then which ones are acting in one?
In 1, G is a subgroup of the permutations. This is a G action. The set is S. S is just a set. So this is an action of G on S. I mean, it is just that. Notice that makes sense because if you take a permutation on S and you feed it X, then you're again getting an element of S, right? And if you sort through it, the identity permutation maps X to X, right? And if you take the composite of permutations, well, it's associative. So that's why number 1 works out. Number 5, I think is a little bit more interesting. We can take the set to be Fn, and we can let the group to be GLN over the field. All right? And then the way A is going to act on X, so here this is an n by n matrix, n by n invertible matrix, yeah? This is a column vector. What do you think the formula for the group action is going to be? Care to guess? Sorry, my stars are getting more and more interesting. Indeed, matrix multiplication is going to give us, how'd that happen? No, where'd the B come from? Yeah, X maybe? Again, to prove that this group action is straightforward. All right, so now there's a theorem. Let G be a group and S a set. Any group homomorphism from G into the permutations of S, right, corresponds to an action of G on S, and vice versa. In other words, every group action produces a homomorphism and vice versa. Now, the proof is missing from my notes because I proved it October 14th of when I wrote these notes, 16. Let's see if we can reproduce the proof today, or at least the heart of the proof, all right? So let's just work on this direction to start with. So assume that you've got a group homomorphism, which would be like what, like something like F mapping from where? From G into the permutations on S. What are permutations on S? These are, phi going from S to S, such that what? What condition do we have on phi? A bijection. Is there anything else? Any other bells and whistles here? There are not. Permutations are just the set of all bijections on a set. Right? It's essentially a blank canvas. I mean, it's got incredible possibilities in the permutation groups. Anyway, so we're given that that's a homomorphism, right? So what does that mean? That means that F of G1, G2, yeah, is equal to, let me use A and B. F of AB is allegedly equal to F of A, F of B. Right? Now, what is that? What does the right-hand side multiplication actually mean? That means composition of functions, right? Because F of A and F of B are permutations on the set S. And we'd like to define what we mean. We want to define a group action of G on S, right? So I need to say, okay, I'm going to take G times X, and what's it going to be? How should I define? What can I make my definition? All I've got to work with is this group homomorphism. What do I have to write down? If you think about it for a second, we've got to write down F of G, right? Because that's the only thing that G can go into. F of G is defined. And what's F of G? F of G is a permutation on the elements of S, yeah? So what can I do with F of G? I can feed this function, right? I can let it evaluate X. If you think through it, that's kind of about the only thing you could write down there. So if this theorem is true, it's got to be something about this thing. Does that work? Does that actually define a group action? Well, how about if we look at E times X, what do you get? You get F of E acting on X, but what is F of E? If F is a homomorphism, a group homomorphism, what's the identity map to? Identity, right? So F of E is the identity on S, which is equal to X again. So there you go, that's axiom 1. How about axiom 2? If I have A times B times X, let's do that one. Well, this is allegedly, I mean, how do you work that out? This is A, I'll do the B one first. That's F of B acting on X, yeah? Which is then, how's that go? Well, that would be F of A, yeah? Acting on F of B of X, yeah? Which by composition of bijections is the same as F of A, F of B acting on X, which by the group homomorphism property is f of AB acting on x, which, by the way, is AB multiplying x by our definition. There you go, axiom 1, axiom 2. We've used the group homomorphism to produce a group action. Now, how do you do the versa of the vice versa? What's the other direction here? So you're given star that goes from G cross S to where? To S again, yeah? You want to produce F, which is a mapping from where? From G to the permutations on S. So you got to tell me what F of G acting on X is equal to. I'm not saying it's the same F we were working with before, all right? I mean, you could put an F tilde here or something if you want. Produce an F tilde, yeah, but I don't want you to logically think I'm still doing this part, but you could think that way. Because what you should see is that there's one thing you got to write down, which is G times X. So if we let that define F tilde, these calculations I just did are reversible in view of that definition, and you can easily prove that F is in fact a homomorphism as required. So there you go, that's that theorem. Sorry, I didn't type it up. All right. So next definition. So the purpose of these examples is just to impress upon you that the concept of a group action is, quite general and covers a lot of ground, some of which we've walked on before. And so here's the definition. Again, G acting on S, G a group, all right? And so number one, we define for each X in the set, all right, the orbit of X under G is this kind of not quite closed circle, X equal to G times X, such that G is in G. So this is the orbit. The orbit is just, you take a point in the set, and then you let everything in the group act on it and see where it goes. That's the orbit. The stabilizer for each X in S, the stabilizer of X in G is G sub X equal to G in G, such that, oh well, G times X is equal to X again. So it's the X which go nowhere. The key first thing you should notice about orbit versus stabilizer is that the orbit, right? G times X, where is G times X? Remember, multiplication does what? And the action goes from G cross S to where? To S again, right? This is a subset of the set on which we're acting. In contrast, the stabilizer is in fact a subset of the group which is acting. Okay? And then finally, there is something else called the subset fixed by subset of S, subset of X fixed by G sometimes denoted S with an upper G, and that's going to be the X in the set such that what? G times X is equal to X for all G and G. So that's a subset. Where's that a subset of? Again, that's a subset of S, but it's a different subset, right? Different than the orbit. We're looking for all X in the set which the group doesn't move. Does that make sense? The fixed subset is the set of all X in the set which the group does not move. The stabilizer is also known as the isotropy subgroup. Also known as isotropy. I can't spell isotropy subgroup of X. Little terminology there. Now, one of the first things we can prove, let's see here. So, example, I mean, you might ask what's the orbit of any of these examples, right? And those are interesting questions to think about. I think the two different actions that we looked at here that I've just erased. So the one of them gives you orbits which are left cosets. The other one gives you orbits which are right cosets. The action, the H action on G, the orbits are actually cosets for those two. All right. Now, here's an easy theorem that makes a great test question. If G X on S and X is an element of S, then Gx is a subgroup of G. Let's prove that. What should we do? First of all, I would point out that Gx is a subset of G by construction, right? By the very way we define the stabilizer, it's a subset of G. So we don't have to worry about that. Yay. Is it non-empty? By axiom 1 of the group action, we have what? That E acting on X is equal to X, right? And that's the condition that we need for it to be in the orbit, right? There exists a G such that, you know, let's see here. So what's this say? This says X itself is in its orbit, right? Wait a minute. I'm sorry. I'm an idiot. Why am I talking about orbits? I mean, it is true that X is in its own orbit, and it's also true that that's the meaning of this equation, but that's not the task at hand, right? Focus. This says what? This says that E is where? In Gx, right? Yeah. I mean, what I wrote down was not incorrect. It was just not correct to our task at hand. Sorry. I'll try to be less of an idiot. So it's non-empty, yeah? And what's next? Let's let A and B be in the stabilizer of X. Consider, what does that give us? Well, let's just write down what that gives us. That gives us that A times X is what? x again, right? And it also gives us that b acting on x is x again. By definition of stabilizer, we have this data to work with. Yep.
Should that then be Axiom 2? Since we're talking about stabilizer.
No, the axiom 1 was that e times x is x again. That was the definition that I erased.
Okay.
The definition of group action itself. I mean, by definition 2, I'm using definition in part 2 to get this implication here. I mean, because, yeah. Okay, so I think here it's easiest to divide and conquer and do the two-step subgroup test, personally. Let me do that. Notice if we take AB and multiply by x, what's that equal to? By the associativity, now this time, Liam, by Axiom 2. By Axiom 2, this is A times B times x, right? Or I would sometimes say by quote-unquote associativity of the group action, but that's not, again, that's an abusive terminology. It's not really associativity. Fine. This is x, right? By assumption, which is again x, which shows you thus AB is an element of the stabilizer. Now we need to show that the inverse, right? Notice that A inverse times A, right, is equal to E. I mean, that's just so like 3 weeks ago, right? And then so A inverse A, I don't know, I'm just stumbling around here. We'll come to it in a second. But if I multiply that times x, that's equal to x, isn't it? Because this is E times x, right? And then that says what? That says that A inverse times A times x is equal to x, right? Which then tells me that A inverse times x is equal to x. I mean, there's various, I think every time I come to this, I'd probably work it out a different way. There's a way. We've just proved that A inverse times x is x again, which shows you that A inverse is where? It's in the stabilizer, right? Therefore, by the two-step subgroup test, we've proved that the stabilizer is a subgroup of the group. For which x? Yeah, any x. That's kind of cool. Next theorem it says that, well, essentially this, if G acts on S, then orbits of X partition S. Moreover, for a finite set, we have that the size of the set is equal to a sum over disjoint orbits. In other words, the size of the set is the sum of the sizes of the orbits which are distinct. Yeah. So here, the sum is over distinct orbits. I mean, the moreover is immediate from the first sentence, right? If we have a partition of a set, that allows us to count things by just adding up the number of things in each subset in the partition, right? So how do you think this theorem is proved? All we need to do is to produce an equivalence relation on the set. What is the equivalence relation on the set which picks up orbits as its equivalence classes? We want an equivalence relation on S for which the orbit of X is the equivalence relation, right, of X, in the sense that it's Y in S such that X is equivalent to Y, right? So you guys tell me, how should I define this equivalence? X and Y are equivalent when? You tell me, X is equivalent to Y if and only if what? Let me start you out. There exists G in G such that what? X is equal to G times Y. I mean, if you look at the definition of orbit that we just gave, I'm really just saying X and Y are equivalent if they're in the same orbit. Is this an equivalence relation? I stumbled into reflexivity by accident here about 10 minutes ago, right? So reflexivity is another way of looking at this equation. E times X, right, equals to X. That is intertwangled with the fact that X is equivalent to X for all X in S, yeah? Maybe let me skip the qualifier because I don't want to put, you're going to have me, to be careful, I'm going to have to start putting qualifiers on everything, and I just don't want to qualify things that way. Pun intended. So there you go. It is reflexive, yeah? How about symmetric? If X is equivalent to Y, that implies that X is equal to G times Y, right? And then here's a calculation that I should have done already. If we multiply by G inverse both sides, yeah, G inverse times X is equal to G inverse times G times Y, right? But by Axiom 2, that's just equal to E times Y, which is equal to Y again, yeah? Which shows you what? That shows you that Y is equivalent to X, right? We can move the G to the other side, which according to our definition says that now Y is equivalent to X. There's symmetry. And transitivity could be proved similarly, all right? Do you need me to go through it, or I'm going to go on? Go on. So we can prove transitivity following similar calculations, and so we have that an equivalence relation on S, consequently the partition of S by the orbits, and the counting follows, yeah? Questions? So then, theorem. If we've got a Gx on S, and if X is an element of S, then the elements of the orbit OX, all right, are in 1-to-1 correspondence with left cosets of the stabilizer of X. Moreover, the size of the orbit is equal to the index of G in, rather, the index of the stabilizer in X, which is to say that the size of the orbit is, again, the index of the stabilizer Gx and G. So this is my theorem 3.6.13. So what do we need to do to prove this theorem? The main claim is that there's this one-to-one correspondence, right? So we need to come up with a function, which is a bijection, right? From the orbit of X. Let's see here. So here's the function I give. I say let F be a mapping from the orbit of X to the factor group. Now, I shouldn't say factor group. I don't mean factor group. It may or may not be the case that G sub X is normal. So in this context, I'm just using G mod Gx to indicate the set of cosets. We can always do that, whether or not there's an allowed group structure there. We can still talk about the set of cosets, all right? So it's not an abuse, just a less structure than we have grown accustomed to lately. And so here's what I say. I say for y in the orbit of X, all right, there exists G and G such that what? Y is equal to G times X, right? So define f of y equal to G Gx. Is this map? And this map is by properties of the into, right? I mean, this is a coset, right? So it's definitely into. Is it single valued? Now, so to test the single valuedness here, the issue is there could be more than one way to get from X to Y. So in the set S, we could think about it this way. We've got X, right? And maybe you've got an orbit. Maybe the orbit looks like that, right? And on the one hand, you could get to Y like here. You could have, you could have Y as G times X, but you know what? Maybe you could also think of it kind of like that if you want to have a geometric sort of. But maybe you could also go like this, you know? And maybe that would be Y is equal to H times X, yeah? Maybe there's two different ways to reach the orbit by different distinct group elements. I mean, that's possible. So this does not uniquely define Y. Excuse me, this is not uniquely, it's not Y. Y is uniquely defined, okay? Y is uniquely defined, rather, because Y is just an element in the orbit. But what's not uniquely defined here is the G. See, because it could be H. We could have Y is equal to H times X, right? And then that would allegedly say f of Y is equal to H times Gx, right? And so if this function is going to be single valued, we had better have that these two are the same coset. Are they the same coset? Well, if G times X is equal to H times X, then what? I believe we'd have X is equal to G inverse H times X, yeah? And that would say that would say what? I mean, maybe we already knew this if I just remember what we just did, which was to prove what? The stabilizer subgroup, right? So, I mean, duh. G is in the stabilizer of X, H is in the stabilizer of X. So of course, G inverse H is in the stabilizer of X. I'm just recovering part of our proof of the subgroup stabilizer subgroup theorem. And what's this say? Oh, remember? What's this say about cosets? This tells me that GGX is equal to HGX, yeah? I think. Oh, sorry. Now, one of the interesting, yeah, uh-oh. I mean that a function is into, that just means that the alleged value for the function at least fits in the codomain. But I don't, when I just say into, I'm not even alleging that the value is a value. It could be like the values of the input are fitting into the codomain. So then I go to check if that actually is if for the rule, is it actually a value or is it a set of values? If it's actually just a value, then it's single valued, right? So there's lots of different things attached to being a function. Like the outputs have to actually be in the codomain. That's what I mean by into. Now, come on. The interesting thing, by the way, you notice that the equivalence relation, does that require finiteness? It doesn't, right? We also have a partitioning of the set into orbits, even in the case that the set is infinite. But in the case that the set is finite, we also have that counting formula, which is kind of beautiful. Now, we're almost done here. If I can get back to my... Come on. So I just got done, I just finished proving the theorem 3.6.30. Well, I've not proved it yet, right? At the moment, I've just shown you, hey, there's this mapping F that goes from the orbit to the cosets, right? We proved that the mapping is into, it's single valued. Oh, you already changed it? Cool. So the rest of the proof that it's a bijection is in here, and it's straightforward to prove that that mapping is in fact a bijection. And once you have that, well, I guess the interesting thing is the counting, right? So the orbit of X is the number of cosets, right? But by Lagrange's theorem, the number of cosets is what? The index, right? Well, and that's not it. I'm sorry. This is just notation. We're not using Lagrange's theorem just yet. Never mind me. I'll shut up. And then that brings us to the corollary, which is actually the orbit stabilizer theorem for which this lecture is named. If a finite group acts on a set S, then the number of elements in any orbit of X must divide the order of the group. Moreover, come on, don't die on me now. The size of the group is equal to the size of the orbit times the size of the size of the stabilizer. This is the orbit stabilizer theorem, right? And the proof is pretty simple. I mean, for a finite group, the number of gx cosets is the order of the group divided by the order of gx. That is Lagrange's theorem, right? So Lagrange's theorem gives us that this is equal to that. But on the other hand, we just found a bijection which says that that's in one-to-one correspondence with the orbit of x. So there you go. The order of g is equal to the order of the orbit times the order of the stabilizer. This is the orbit stabilizer theorem. Now, here's a interesting, perhaps, application of that. If we look at the vertices of the square as the set, all right, and think about D4 acting on that set, right? That defines a natural action. Because if D4 acts on the vertices of the square, it takes the vertices of the square to the vertices of the square. So it's definitely going to give us, you can work it out. It gives us a group action. And so let's see here. The orbit, for example, of V0, which is that vertex, right? If you look at rotations, where does that vertex go? It goes everywhere, right? So that means that if you have an orbit which covers the whole set, then the group action is said to be transitive. Right? If there exists a G such that the orbit, if there exists an X such that the orbit of X is the whole set, then that's a transitive action. This action is transitive. So then, if that's the orbit of V0, which of the elements in D4 fix V0? Which of the stabilizer? What's in the stabilizer of V0? Nothing up here, right? Looks like this, going from here to here, is in the stabilizer. Let's see here. Oh, it's easier to see in the cycle notation. What stabilizes V0? You can see it here, right? If V0 is not moved, it's stabilized, right? So, not in the stabilizer. Oh, in the stabilizer. Not in the stabilizer. Not in the stabilizer. That stabilizes V0. Doesn't stabilize V0. Doesn't stabilize V0. That one stabilizes V0. So, in short, how many things do you guys expect are in the stabilizer by the orbit stabilizer theorem? The orbit's got 4 things. How big is D4? 8. So how many things should be in the stabilizer? 2, and that's what we just counted. There were 2 things that stabilized V0. So, and you could work similar things. Now, I need to make a correction here before you get confused about it. In this next example, which is a more powerful example, we study the symmetries of a cube, all right? And I say if you look at the face, you've got 6 faces, and you can think about, isometries which move the faces to the faces. And if you think about a particular face, I say that the stabilizer has order 4. So what I'm thinking about there, I've neglected the motions which correspond to taking the cube and turning it inside out. All right. So if you did those, if you also included those kinds of isometries, all right, then you'd actually have the stabilized gx is equal to 8, because basically you get a full copy of D4 for the as a stabilizer of the face. But if we reject those, all right, if we just think about the motions which are physically possible as rigid motions, right, the ones which don't turn the cube inside out, which is not possible to do in 3 dimensions, right, then those are called motions. So motions are actually physically possible isometries. There is a set of isometries which are not physically possible because they involve ripping shapes inside out. The full isometry group includes those. If we reject those, instead of saying symmetries here, according to my definition, I really should just say motions. Cross out symmetries and write motions here, then that actually makes sense. If you go symmetries, that should be 48, because this should be 8. So anyway, with that, have a good break, guys.